This lesson is all about vectors in the plane. So it's accepted that there are simply different types of quantities that we're going to run into either in nature, in a physics class, or a chemistry class. Any type of class we run into, there are different types of quantities. The types that we're going to look at are scalar quantities versus vector quantities. A scalar quantity is a single real-valued number that usually represents a magnitude. So for instance, volume, mass, temperature, length, all of these are scalar values. They're simply one number which represents the magnitude of a measurement. A vector, however, is a quantity that represents both magnitude and direction. So this is represented by a directed line segment that has an initial and a terminal point. So for example, velocity, force, acceleration, all of these quantities in physics, but it's not restricted to physics obviously, are vector quantities. So the representation of vectors. So graphically we have a vector is a directed line segment, which you can think of as just a line with an arrow. It has an initial point, which we generally will call P, give it some label, maybe describe it by the coordinates of that initial point, and a terminal point, which you can label as well and give it coordinates if you need to. And you can label the vector with the notation of putting your initial point first, then your terminal point, and an arrow on top of the letters. So vectors represent magnitudes and direction. So let's look at how we would come up with the magnitude of a vector. If we know the initial point's coordinates and the terminal point's coordinates, we can use the distance formula to calculate the magnitude. So that's going to give us the length of the vector. The length of the vector is its magnitude. The length or the distance between 2 points would give us the length or the distance between them. And notice the notation. I've put absolute value bars around the name of the vector. That is one way of indicating that you want to do a magnitude of the vector. The direction of a vector comes from the relationship of the tangent of the angle measure is equal to the effectively the slope of the line passing through the 2 points, the initial and the terminal point. So you could calculate the angle theta by using this formula along with an arctangent. Two vectors are called equal if they have the same magnitude and direction. Let's try an example. So determine if the vectors described below are equal. Sketch the vectors on the graph provided. So I have vector 1 defined by the points P and Q, and vector 2 defined by the points A and B. I'm going to see if first their magnitudes are equal, and if that's the case, I will take a look at their directions and see that they're equal as well. Let's see what happens with magnitudes. So the magnitude of vector PQ is going to be the square root of, according to the formula, I take x2 minus x1 quantity squared. So in this case it would be 8 minus negative 4, so that's plus 4 quantity squared. And then I'm going to take the difference of my y values, so 7 minus 5, and square those. So 8 plus 4 is 12. When I square that, that's 144. 7 minus 5 is 2. When I square that, that's 4. So I get effectively the square root of 148, which I'm certain could be reduced, but I'm not going to worry about reducing it at this point because I just want to compare it to the length of the other vector. So let's calculate that length. So vector AB so I would take x2 minus x1, so that would be 3 minus negative 6, so 3 plus 6, quantity squared, plus negative 5 minus 3, quantity squared. Let me get a little bit more room here. Three plus 6 is 9. When I square 9, that's 81. Negative 5 minus 3 is going to be negative 8. When I square that, that is 64. And so when I take 64 plus 81, I get 125. Which again, I could easily reduce that one. But the point is it does not have the same magnitude. I can clearly see that by comparison. It's very close, but they're not equal. So since those magnitudes are not equal, we can definitely say that vector PQ is not equal to vector AB. I would like to go ahead and graph them though, so you can see the vectors on the plane. In order to graph them, I start plotting the initial point. So point P is negative 4 and positive 5. Should be right there. Point Q is 8, 7. Should be right there. And I draw an arrow between them, and that gives me my vector. Okay. Vector AB, it's negative 6, positive 3, is the location of point A, my initial point. B is 3, negative 5. And it's right there. So these obviously don't have the same direction either. So neither the magnitude nor the direction is the same, and therefore these are definitely not equal to each other. Vector addition. The sum of two vectors is also a vector. There are two ways of graphically representing the sum of two vectors. One way is called the tail-to-tip method, and in the tail-to-tip method, you take your two vectors, you take vector A, so I'll highlight vector A here in green, and you take vector B, and you orient it so that the initial point, the tail of B, is at the terminal point, the tip of A. So you arrange them in that respect. And it's fine to move any vector that you want around the plane, because according to the last definition, two vectors are equal if their magnitude and their direction is the same. It doesn't matter where they're located in the plane. So you're free to move a vector anywhere you want as long as you don't change its magnitude or direction. Now the sum of these vectors that I've got in red is this vector right here, which goes from the tail of A to the tip of B. Another way to think about this is the parallelogram rule, where you arrange vector A and vector B so that they have a common initial point, and you create a parallelogram using lines that are the same length and the same direction as the original vectors that you start with, and you create the diagonal of that parallelogram. The diagonal is the sum of those two vectors. So graphically, that's what is always going to happen with the sum of vectors. In terms of vector subtraction, it's essentially the same as vector addition. You just end up with the opposite diagonal of the parallelogram. So for instance, if A and B are oriented so that they have a common initial point, and you draw the parallelogram that is, the same, has sides that are the length and direction that are the same of the original two vectors. Vector A minus B is just the other diagonal in this parallelogram. Note the orientation of it, however. It's going downward in this case. And to understand why that is, let's look at what happens when you evaluate negative b. So what happens is it just points the vector in the opposite direction. And a minus b is essentially the same as a plus negative b. So if we just reposition vector b so that it's negative b, so if this is originally vector b, negative b just points in the opposite direction. A is still in the same place. Here's my parallelogram. And the sum of those vectors now would be that vector right there, which if I retranslated this vector that I've colored in green, it would translate right back up here. So this is the vector A minus vector B. Scalar multiplication. If a vector is multiplied by a scalar value, it only affects the length of the vector, not the direction. So if I have vector u, which is some given length and direction, and I multiply that vector by a scalar value, it's only going to double the length of the vector. The direction stays exactly the same. Similarly, if I take 1/2 of u, it's just going to reduce the length of the vector by 1/2. It doesn't change its direction. Negative u technically does change its direction, but it's in the opposite direction. 3/2 of u, it would increase the u by a factor of 1/2 basically, but it still points in the same direction. All of these vectors are parallel to one another, so that's what's important to remember when you're dealing with scalar multiplication. Let's work an example. So find the magnitude of the resultant force for the two forces shown below. So I have two forces that are acting on a point. So I'll call this point P. And what's happening is there's a force of 80 newtons and a force of 110 newtons that are acting on this point, but in different directions. So the resultant of the forces comes from effectively adding these vectors together. And in order to add these vectors together, we're going to have to either use that tail to tip method or the parallelogram rule. I tend to prefer the parallelogram rule myself. So what that would look like is, just draw the best parallel line to one of the vectors and then to the other. Get them to meet up in the right spot. And when you connect the diagonals, that gives you the resultant vector. And that's what I'm looking for. And I want to know the magnitude of this force. So all I need to know is a value in newtons. I don't need to know individual angle measures that to work this out. Which is good, because I think that's going to be a little bit more complicated of a problem to solve. Although it's reasonable, we can do it. But this one is quite a bit simpler. And here's the reason why. So when you have a transversal cutting parallel lines, so here's parallel lines and I have a transversal. The opposite interior angles are equal. Okay, so these two would be equal and the others that I marked are equal. and the opposite exterior angles are equal as well. So there's lots of equal things when you have transversals cutting parallel lines. So right here, just think of these as parallel lines, and then you have a transversal cutting it. So what that means is this 60-degree angle is equal to this 60-degree angle. And if you know that that's 60, then you also know that this is 120 degrees. So keep that in mind when you're solving problems. A lot of problems are solved using that trick of opposite angles through a traversal are equal to each other. Now, since we know that, we have basically one triangle that I'm looking at right now. This is my triangle. I'm going to color it in green. So just so you know the triangle I'm referring to. So I know one side of the triangle is 80 newtons. I know an angle measure inside that triangle. And I also technically know this side over here is also 110 newtons because it's parallel and so it's equal in length to the opposite side. So that gives me a situation where I have two side lengths and an angle in between. So that is the side angle side case, which is solved using the law of cosines. So I would take c squared, set that equal to 80 squared plus 110 squared minus 2 times 80 times 110 times the cosine of the angle in between. And in order to solve this, I'll need a calculator. Okay, so I'll take 80 squared plus 110 squared minus 2 times 80 times 110 times the cosine of the angle between, which is 120 degrees. And I should verify, yes, I am in degree mode. Okay, so I should be good. This is initially my answer, but I need to take the square root of that because that's equal to c squared. Oops. Second and negative. And I will round this to the nearest whole number and say c is approximately 165 newtons in this case, since we were talking about measures of force. An airplane is flying at 525 miles per hour on a bearing of north 25 degrees west. It encounters a wind that is blowing 45 miles per hour on a bearing of north 70 degrees east. What is the resulting speed and direction of the plane? All right, so I'm just going to draw a point somewhere, and that's going to be my initial position, and base my bearings off of that. So the plane initially is traveling north 25 degrees west. So I'll draw a north-south line here. And if it's going north 25 degrees west, just recall your, compass readings here. So north, south, west, and east. It's very tempting because you say north, south, east, west to put east on the wrong side. Just make sure you get that straight. So it's going 25 degrees toward the west. So that means the airplane initially is going this direction. So 25 degrees west. Okay. Now, it encounters a wind that is blowing 45 miles per hour on a bearing of north 70 degrees east. So, I need to write in this is 525 miles per hour. So the next bearing is north 70 degrees east. So 70 degrees east would be like that approximately. So it's going to go that direction. And it's 45. So what is the resulting speed and direction of the plane? So the resulting speed and direction of the plane is going to be this line here that I'll put in green. Because the idea is the plane's trying to move in the north 25 degrees west, but it's being hit by a force of wind from 70 degrees, and so it's kind of pushing it more toward the east. So we want to figure out what the resulting direction is. We'll answer that direction as a bearing, and we want to know what the resulting speed is. So let's see what we can do. Now, most of the time, these types of problems come down to measures using finding the angle of measures using transversals of parallel lines. So let's see what we need to do in order to solve this problem. So the parallel lines that we'll work with are always the north-south lines. And I'm going to extend it just so you can see how I'm looking at this. Now, the north-south lines that I have a transversal, and that transversal is the length 525 that I'm looking at. And this angle measure off north is 25 degrees. So this angle measure is also 25 degrees. So that means this little sliver is 25 degrees. Now, I happen to know the 70-degree angle and the 25-degree angle. Since this is a straight, they're together on a straight line, I can figure out that third angle in between. If I just take 180 minus 25 minus 70. So that's going to be 85 degrees. So this angle measure here on the inside, I'll put in green, is 85 degrees. Now that's an important one. The reason that one is important is because if I kind of, increase the scale of what I'm looking at. All right, I know this angle measure right here is 85 degrees. I know this side length up here is 45, and this side length down here is 525. So I have the side angle side case, which I can solve with the law of cosines. And that's going to tell me what this right here is. So that's going to be my resultant speed. So that is extremely helpful. That's pointing us in the right direction. Since I have my diagram still, I'm going to erase, well, actually, I'll leave it up and I'll go and solve down below using the law of cosines. So it's going to be c squared is equal to 525 squared plus 45 squared minus 2 times 525 times 45 times the cosine of the angle between, and I get the calculator out, bring it over here so it's not covering my work. Okay, so 525 squared plus 45 squared minus 2 times 525 times 45 times the cosine of the angle between, and I need to take the square root of that number, so 523. So this isn't really affecting the speed very much. It's only decreased it by 2 miles per hour. The thing that we do need to figure out, however, still is the resultant angle measure. Now, because I know this over here is 523, I know a little bit more about this triangle than I did before. And I'm going to put that over here so that you can help follow along as to how I'm solving this, because now I'm really just concentrating on this triangle. So if I could come up with some of the remaining angles in this triangle, I could then determine what the new bearing is. In particular, I think if I knew this one, that would probably be the most important one to solve. So I'll call that, well, I guess if we've been using uppercase letters for angles, I'll call it A. Well, sorry, I just know if I erase, it's going to erase the whole thing. There. So let's see what we can do. I believe we could solve for that using the law of sines. So what I will do is take the sine of A divided by 45 and set that equal to the sine of 85 and put it over 523. Now, if I solve using the law of sines, I have sine of angle measure A is 45 sine 85 degrees divided by 523 degrees. Let's see what happens. So 45 sine 85 degrees divided by 523, get 0.0857. I do need to take the arc sine of that. So 4.9. Now I'll just take it to one decimal. Now that's not my new bearing, because let me show you where that is on my chart. So angle A is this right here in my chart. So that's 4.9 degrees that way. It was 25 degrees for that complete bearing, so this angle measure right here, which is the new bearing, I'll call B, is going to be 25 degrees minus 4.9 degrees, which would be 21.1 degrees is the new bearing, which we need to state as north 21.1 degrees west.